Why are you not sinking through the floor right now? Why can you push a door or feel the roughness of a surface? The classic answer speaks of forces, invisible forces acting at a distance. But modern physics has revealed an infinitely stranger and more fascinating truth. The reality you perceive as solid and continuous is, at a fundamental level, a relentless simmering of phantom particles, a continuous exchange of ephemeral messengers that weave the very fabric of the universe. What you are about to discover is not science fiction, but the most precise and powerful theory ever conceived by man. It is the jewel of physics, quantum electrodynamics, or QED, and it will forever change the way you see the world. Before we dive into this abyss of knowledge, a small gesture from you can make a huge difference for us. If you love science and discovery, subscribe to the channel and activate notifications. So, what is quantum electrodynamics? In simple terms, it is the theory that describes how light and matter interact. And this interaction, my friends, governs almost the entire universe we know, excluding gravity and nuclear forces. Let's start with a simple example. Take two electrons. We know that, both having a negative charge, they repel each other. Classical physics would call it the Coulomb force, an invisible action at a distance. But QED tells us that there is no action at a distance. That repulsion is actually an exchange. The electrons talk to each other by throwing a particle, a virtual photon. It is this exchange that generates what we perceive as force. This mechanism is the basis for the solidity of matter, for why we don't sink through the floor, for friction, for almost all the forces we experience every day. To arrive at this revolutionary understanding, the journey was long. It all began at the dawn of the 20th century, when Max Planck, studying an idealized object called a black body, ran into a seemingly insurmountable problem: the ultraviolet catastrophe. His calculations went haywire, predicting an infinite emission of energy. To solve the paradox, Planck was forced to make a radical hypothesis. Energy is not continuous, but is emitted and absorbed in discrete packets, in quanta. A few years later, Albert Einstein reinforced this idea by explaining the photoelectric effect and demonstrating that light itself is made of these packets, which we now call photons. Energy exists in coins of fixed value. You cannot have an arbitrary fraction. However, a theory was missing that could bring together these scattered pieces with Einstein's special relativity and the nascent quantum mechanics. The first giant leap was made by Paul Dirac in 1928. His famous equation not only described the electron in a relativistic way and introduced an intrinsic property of it called spin, but it also hid a shocking surprise. It allowed for solutions with negative energy. Dirac, with incredible audacity, did not dismiss this oddity. He interpreted it as the existence of a new particle, identical to the electron, but with the opposite charge, the positron, the first particle of antimatter. A few years later, in 1932, Carl Anderson observed it in cosmic rays, confirming Dirac's brilliant intuition. The path seemed clear, but a new, terrifying obstacle emerged. When physicists tried to make more precise calculations about the interactions between electrons and photons, the results were always and only one thing: infinity. It was a disaster. The theory, which seemed so promising, broke down as soon as one tried to add the details. The idea is this: an electron traveling through space is never truly alone. The quantum vacuum is not empty. It is a swarm of virtual particles that continuously appear and disappear. The electron is therefore constantly dressed in a small cloud of these virtual particles, which alter its properties, such as its mass. When they tried to calculate the contribution of this little cloud, the result was infinite. The solution, found in the 1940s by brilliant minds like Feynman, Schwinger, and Tominaga, was a mathematical procedure as bizarre as it was effective: renormalization. In practice, physicists realized that the bare mass of an electron, the one without its little cloud, is a purely theoretical and unmeasurable concept. The only thing we can measure is the dressed mass. They therefore decided to hide infinity under the rug, absorbing it into the value of the mass and charge that we measure experimentally. It may seem like a trick, a mathematical sleight of hand, but it works perfectly. Thanks to renormalization, QED became a predictive machine of astonishing precision, capable of explaining subtle phenomena such as the Lamb shift and the magnetic moment of the electron with unprecedented accuracy. Those were the golden years of the theory. To visualize and calculate these complex interactions, Richard Feynman invented a brilliant tool, the diagrams that bear his name. These diagrams are much more than simple drawings. They are a shorthand for the quantum world. Imagine an electron and a positron meeting. In the diagram, you see their lines converging. At the meeting point, they annihilate, and from their union, a virtual photon is born, represented by a wavy line. This photon travels for a brief moment and then materializes into a new pair of particles, for example, a muon and an anti-muon, whose lines move apart. Every line, every vertex of this diagram corresponds to a precise piece of a mathematical formula. A key concept in these formulas is the propagator. The propagator is a mathematical object that describes the probability amplitude for a particle to travel from a point A to a point B in space-time. Unlike the old wave function, the propagator contains the entire history of the particle, its starting point and its destination. I understand that the complexity of this theory may seem daunting. It is abstract mathematics that describes an invisible world. Now, beyond physics and mathematics, what are the implications of all this for our conception of reality? Here we enter a fascinating territory where science borders on philosophy. Remember, what follows is not part of proven scientific theory, but are the reflections and speculations to which this theory pushes us. First, the nature of the vacuum. The vacuum is not empty. It is not nothingness. It is a dynamic arena, a boiling ocean of potential, where virtual particles are born and die in a flash. The matter we see, the real particles like electrons, are nothing more than more lasting excitations of this fundamental substrate, like waves on the surface of this quantum ocean. The distinction between being and non-being becomes blurred. Solid and stable reality is an illusion that emerges from a fundamental chaos. Second, space and time. The idea of the propagator, which must take into account all possible paths to calculate a particle's journey from A to B, overturns our idea of a single, defined trajectory. Furthermore, in Feynman diagrams, antimatter, like the positron, can be mathematically described as a normal particle traveling backward in time. This does not mean we can build time machines, but it suggests that at a fundamental level, the arrow of time as we perceive it may not be so absolute. Third, and here we are in the purest speculation, consciousness. QED, like all of quantum mechanics, is an intrinsically probabilistic theory. It does not tell us what will happen, but only what the probability is that something will happen. This has led some thinkers to wonder if this fundamental indeterminacy of nature leaves a space, a crack, into which consciousness could insert itself. Is reality purely mechanical and random, or is there a deeper level where information, and perhaps the observer, plays a fundamental role in collapsing the infinite possibilities into a single manifest reality? These are abyssal, unanswered questions, but modern physics forces us to ask them. In conclusion, quantum electrodynamics is much more than a successful theory. It is a window into a reality radically different from the one our senses present to us. It has shown us that forces are exchanges, that the vacuum is full, and that particles are excitations of invisible fields that pervade everything. It has forced us to give up our most ingrained intuitions about what is solid, what is empty, and even what is real. It is the unified language of light and matter, a mathematical tale of astonishing precision that describes a universe that is dancing, probabilistic, and infinitely stranger and more wonderful than we could have ever imagined. If this journey to the edges of reality has fascinated you, I invite you again to support this project. Subscribe, leave a like, a comment. Thank you for traveling with us. Until next time.